Hi everyone, welcome back. In this video we're going to take a look at some transformations, and we'll wrap up our transformations unit looking at what happens when we have multiple transformations in one function. So what happens when we have translations and also stretches or compressions both in the same direction. So in the last video we looked at all kinds of transformations, stretches and compressions, so multiplying, and then also translations, adding or subtracting either to the input or to the output. When we see both stretches and compressions and translations in the same function, we need to be very careful of the order that we apply these transformations. So it's really important that we keep track of the order that these transformations were applied in, because if we apply these transformations in the wrong order, then we'll end up graphing the wrong function. So we really need to be careful about thinking about what steps and what order do we need to take to transform our parent graph into the function that we're given. Let's take a look at a quick example. So let's look at the graph, or the function f of x is equal to 2x plus 3 squared. So here we have a quadratic. We'll end up with a parabola. Our parent function, in other words, the function without any transformations, we could call that g of x is equal to just x squared. So that's our parent function. And what we want to do is go through the steps of how we got from x squared to 2x plus 3 squared. Okay, so first off, we have g of x equals x squared. The first thing we could do is apply our translation. So we're going to be translating our graph 3 to the left. So an intermediate step, we have g of x plus 3, which is just x plus 3 squared. Okay, so here we're just taking x plus 3, or sorry, we're taking x squared and we're translating it to the left. So if we first graph g of x, which is x squared, sketch a quick graph of that. 0, 1, 1, 2, 4, negative 2, 4, and so on. So here's our graph of g of x. We are first translating to the left 3. So our first transformation is going to be to push the graph to the left 3. So we'll end up at negative 3, 0, negative 2, 1, negative 4, 1, negative 5, 4, negative 1, 4, and so on. So here's our first transformation. Next, what we're doing is we're taking our x and we're going to be multiplying it by 2, g of 2x plus 3. And that gives us our f of x. So that's also going to be our final graph. So we have a compression by 2. In other words, we're taking our graph and we're compressing it. In other words, taking all of our x values and compressing it by a value of 2, or dividing all of those by 2. One quick note, so we went to the left 3 here because when we're doing horizontal translations, as a reminder, we're doing the opposite of what we see on the inside. So x minus negative 3, so to the left 3. Similarly, for stretches and compressions, if we have a number greater than 1 that we're multiplying x by, then we're actually compressing it. If it's in between 0 and 1, then we're stretching it. So we're compressing by 2. That means we take all of our x values and we divide them by 2. So negative, instead of negative 3, 0, we have negative 1.50. We have negative 1, 1, negative 0.5, 4. On the left, we have negative 2, 1, negative 2.5, 4. So our graph is a lot skinnier now. Okay, so this red graph is our final graph of f of x, and we went through each transformation individually. So here the order is important. What I want to do next is take a look at what if we did a different order. So what if we decided to compress by 2 first? So compression by 2, g of 2x. In other words, we have 2x squared. So if we compress by 2 first, then our graph would move closer together, so it becomes skinnier. And our second step would be that translation. So we would shift left 3. In other words, we're taking g of 2, and then instead of x, we're replacing it with x plus 3. So here, the order matters because we've already multiplied by 2. So if we've already multiplied by 2 and we change the input, we need to change the entire x that we have left over. So when we shift left 3, we're adding 3 to x, or subtracting -3, and we need to replace this entire x by x plus 3. So here we actually end up with a function that's different than f of x. We have 2 times x plus 3 squared. So we run into a problem when we switch the order. The difference is, so here we added 3 first, and then when we compressed by 2, we multiplied whatever x we had by 2. So the 3 was unaffected by that multiplication. Whereas down here, the 3 is being multiplied by 2 also. One workaround that you could do is to match it up with f of x. We could shift to the left 1.5, because notice if we have g of 2 times x plus 1.5, oops, this should be squared. If we were to distribute that 2, we would end up with 2x plus 3 squared, which is f of x. And this makes sense because we have a skinnier graph, and then also notice that our final ending point is at, or vertex is at -1.5, so we have that shift to the left 1.5. So here the order matters. When we make a change to the input, we need to make a change to or replace the x in our equation with that change. And the order that we make those changes makes a difference. So here it's important that we first shift to the left 3, and then when we compress, we're only compressing x, so we're changing x with 2x. Let's take a look at another example. So next up we have, let's do f of x again is equal to square root of 1 minus x. So here we have a square root function. Our parent function would be, let's call it g of x again. G of x equals square root of x. It's our parent function. And now we need to identify what transformations did we apply to this function. I'm going to start off by graphing g of x. We just end up with one arm of a parabola, and it's kind of like our x squared but sideways, and we only have the positive arm. So just like that. I'm going to rewrite f of x to make it a little bit more clear what's happening. So I'm going to place our x in front. We have -x plus 1, which we could also write. Notice we're just taking x and we're multiplying it by -1. -1 times x plus 1. Okay, so here we can see that the -1 is only being applied to the x. So we want to go ahead and do our transformation first, like we did in our previous example. So to start off, we're looking at a translation or a shift to the left 1. And again, it's the opposite of what we see on the inside. We have -1x minus -1. So translation to the left 1. In other words, we're taking g of x minus -1 plus 1. So g of x plus 1 gives us square root of x plus 1. And if we were to graph that, let's graph this in orange, we're just moving everything to the left 1. So our graph looks like this. So same exact shape, just moved over to the left 1. Our next step, and our final step in this case, would be to apply our multiplication. Because we're multiplying by 1, we're not actually changing the shape of our graph. The negative means that we're doing a reflection, however. So the shape of our graph is the same. We're not stretching or compressing it, but we are going to reflect And it's a horizontal reflection because we're multiplying the input. So we're going to reflect across, if it's horizontal, it's across the y-axis. So g of -1 times x plus 1. So we replaced our x with -1 times x. So here's where the order matters. In this case, because we translated first, the -1 doesn't apply to what we're adding or subtracting. And this gives us our f of x, -x plus 1. So our final graph would be, well, we take our orange graph and we flip everything across the y-axis. So instead of -1, 0, we have 1, 0, 0, 1 remains the same. And then we have -3, 2, and so on. So our final graph looks something like this. Okay. So same shape, just flipped and then moved, well, we moved it to the left one and then we flipped it. So our final ending place for, you could call this starting point, kind of like the vertex, 0, 0 is actually going to be at 1, 0. And here again, the order does matter. If we were to reverse the order, we would end up with, I think, a -1 inside. So we do need to be careful about the order that we make those transformations in. All right, so I want to take a look at one more example, and that is f of x equals 3 divided by x plus 1. Okay, so in this case, we have a reciprocal function. X is in the denominator. So our parent function is just going to be g of x equals 1 over x. So that's the function we start off with without any transformations. I'm going to start by graphing this function. So here we have a reciprocal function. We're going to end up with two curves in the first and third quadrants. And a couple of our points, we have 1, 1, we have 2, 1/2. Kind of goes down like that. And 1/2, 2 is also another point. And then we have the exact same curve, but down here. Okay, so we have two curves in the first and third quadrants, and that is for g of x. So here we need to think about the transformations that we're applying, and we need to think about the order that we're applying in. Notice that we multiply by 3, and we're multiplying the outside, we're multiplying the entire function, g of x by 3, because our 3 isn't in the denominator. Instead, it's in the numerator. So we're multiplying the output by 3. So this is going to be a vertical stretch in this case. So if we multiply the output by 3, we want to do the multiplication first, and then we want to add on the 1. Because if we add the 1 on first, then when we multiply by 3, we need to multiply both terms by 3. And that'll kind of like mess up our translation. So let's take a look at that order that I just mentioned. First, we're going to do our multiplication. So we're going to take 3 times g of x. In other words, we have 3 times 1 over x, or 3 over x, so multiplying the output, and we have a vertical stretch by 3. Okay, and we'll graph this in orange. So all of our y values are just multiplied by 3. So instead of 0.2, or sorry, instead of 0.52, we have 0.56. Instead of 1, 1, we have 1, 3. Instead of 2, 1/2, we have 2, 3/2. So our function kind of looks like this. And then same thing down here, everything is multiplied by 3. So we just kind of reflect those points. Oops. -3, -2, -3/2. Okay, so vertical stretch by 3. Then our second transformation is we have we're adding 1. We take 3 times g of x, we're taking our previous one, and then we're adding 1 onto our function. So we get 3 over x plus 1, which is f of x. That's our final function. So here we have a vertical shift up 1. So we take all of our y values, move them up by 1. So we end up with 0.57 on our graph, and I'll graph this in red. 0.57, 1, 4, 2, 2.5, and so on. So it's going to be our orange graph just shifted up, kind of like that. And then same thing down here. All of our negative values go up by 1. So 0.5, negative 0.5, negative 5, negative 1, negative 2, negative 2, negative 0.5. And so here our graph is shifted up 1. So the red values are the f of x values. In other words, the graph of f of x. So here the order, again, does matter. We first applied a vertical stretch by 3, we multiplied the output by 3, and then we added 1 to that output. So both of these are vertical transformations, you might notice. I want to take a quick look at what happens if we did the opposite order. So if we decided to first shift up 1, then we would have g of x plus 1, which gives us 1 over x plus 1. Okay, great. We know that we end up with a plus 1, so that's a start. We could start by shifting everything up by 1. We do run into an issue, though, when we apply our second transformation, which is a vertical stretch by 3. Because if we multiply by 3, if we multiply the previous function by 3, we need to multiply 3 times the entire output g of x plus 1. So here we have 3 times that entire expression, 1 over x plus 1. So we end up with 3 over x, but we also need to distribute our 3. So you run into an issue here because our transformation, or our translation is too high. In this case, we don't end up with f of x. Similar to before, you could correct that by doing a vertical shift up by 1/3. So you end up with 1. I find it easier to just do our stretch first and then do our translation secondly. So it is really important we think about the order that we're applying them in, because the order does matter when we have multiple transformations. If you're ever unsure, writing it out like this, so I wrote out both examples, can make it a little bit clearer. You'll notice in one of them that you end up with a number that's off or not similar to the final f of x that you should end up with.